4.2 Logarithmic Functions, Day 1 and 2. Your learning goals are that you'll be able to interchange exponential and logarithmic forms, evaluate logarithms, use basic logarithmic properties, and graph logarithmic and natural logarithmic functions. So in the previous lesson, we learned about exponential form. And it looks like y equals b to the x. And in the previous lessons, we learned about how to find the inverse, which is when you switch x and y, and you would solve for y. However, sometimes it's hard to find out what this exponent is, so we use logarithmic form to help us solve this type of problem. So to solve for y, we would do y equals log of base b of x. So y is actually the exponent that you're looking for. B is your base. And x, that's the answer. That number that came from here. So that's what we're going to be doing today, learning how to go back and forth and interchange. In example 1, we're going to write the equation in its equivalent exponential form. Right now it's in log form. So remember, this number is actually your exponent. 2 is your base. And 64 should be your answer when you write it in exponential form. So it would look like this. 2 to the 6th power equals 64. Or you can write it as 64 is equal to 2 to the 6th power. In the example 2, we're going to write the equation now, and it's an equivalent log form, because right now it's in exponent form, where 5 is the base, 4 is the exponent, and 625 is the answer you should get from multiplying 5 by itself 4 times. So remember, you write exponent 4 is equal to log base 5 of 625. Or you can rewrite it the other way. Both forms are correct. Example 3, we're going to evaluate each expression without using a calculator. Okay, so now we are trying to find y. Remember earlier when I said x equals log, x equals b to the y. Our job now is to find that exponent. So when you see log base 2 of 16, you're saying 2 to the what power is 16? And the only number that can possibly be is 4. For b, you're saying 7 to the what power is 1 over 49. Well, since it was 1 over 49, your exponent has to be negative because it's on the bottom. Now we know 7 to the 2nd power is 49, which means 7 to the negative 2nd will be 1 over 49. So that exponent has to be negative 2. Now we're doing 25 to the what power will give you 5. Well, you have to think backwards. We know that 5 squared would be 25. So if they have made your base now the larger number, then the exponent has to be a fraction. And instead of it being 2, it will now be 1 over 2. So these are little things that will help you. And then the only base that we won't see is 10, because our calculators are based on base 10. Everything we do in the numbers in our numerical system is based on base 10. So it's understood. So you're saying 10 to the what power is 100? Well, that has to be 2. And all you have to do is count the zeros. That'll help you. Okay, example 4, we're going to evaluate more logs and simplify without using a calculator. But I'm going to go over some basic properties that will help you. So anytime you have the base of a number and you're raising it to the same number, you're taking the log of base b of b, the answer is always 1, because anything raised to the first power is always itself. And then the second property is when you're taking the log base b of 1, the answer is always 0, because any number to the 0 power is always 1. You have to remember now, these are your exponents. So you're raising b to those powers to get these answers. And then b represents your base. And then the other two properties, the third one is when when you have the log base b of the same base, the answer is always the exponent, which in this case is x. So whatever your exponent is, that's the answer. So you don't have to solve these and try to work them out. And then the last property is when you have base b and you're raising it to the log of the same base, the answer is always whatever this number is. So let's try some to see if we understand our properties. Okay, for A, log base 7 of 7. Remember, when the bases are the same, the answer is always 1, because 7 to the first power is 7. B, log base 5 of 1. The only exponent that can give you 1 would be 0, because 5 to the 0 power is 1. C, whenever the bases are the same, remember the answer is always the exponent. D, when you have a base and you're raising it to the log of the same base, the answer is always whatever that number is. E, now I threw in E just to see if you remember. When you don't see a base, it's always 10. So you're saying 10 to the what power is 1,000. All you have to do is count the zeros, and that'll help you. F and G. Remember earlier when I said that right above the LN key is E to the X? LN and E are inverses, which means whenever you see LN, the base is always E. But they're not going to write it, but it's understood. So anytime that happens, see how the bases are the same? Again, the answer is always the exponent. And same for G. The only difference is you have that e to the 7th is in the denominator, which means your exponent has to be negative. So if you want to rewrite it, you can. So it looks like this. So remember, when the bases are the same, the answer is always the exponent. Okay, now it's time to graph the logs and the natural logs. These are your two general forms that you would see. Now, because logs and exponential forms are inverses of each other, everything is going to be a little bit different when you graph. So when you graph, you only need 2 points to graph. And those 2 points are 1, 0, and B, which is your base, and 1. So those are the 2 points that you're going to start with. And then you're going to use transformations. So you will, now we use transformations. With A, H, and K. Just to remind you, A represents your vertical stretch or shrink. H moves it left or right. It's always opposite. And K, of course, moves it up or down. So the A affects the Y coordinates. Then another thing you need to know is you're going to have vertical asymptotes now instead of horizontal. And they will always be X equals H. Your domain now, or I should say, let's go to range, will now be negative infinity to positive infinity. So that's something that changed. And now your domain, because you have a vertical asymptote, will be either H to infinity, so if it's on the right side of the graph, or it could be negative infinity to H. And your graphs now, since they have a vertical asymptote, are going to curve downward like this. I wanted to start off with this graph so you can see and understand the value of K versus A. First of all, when you see plus or minus, this is K, and you need to rewrite this so it's in the right form so you don't get confused. A will never be added or subtracted. It's always multiplied. All right. So, for this graph, good thing is you don't have to plug in any values. Your 2 points, remember, are always 1, 0, and your base and 1. Well, in this case, your base is 2. So we're going to start off graphing those 2 points. Okay? And then we're going to shift them. There's no A. Left 1 and up 2. And notice now, our asymptote is going to be X equals negative 1. That's why we're moving everything left 1. So at negative 1, you're going to have a vertical asymptote. So I'm going to take these points that I plotted, and I'm going to go left 1, up 2. Left 1, up 2. So when you curve your graph, you're going to curve it towards the asymptote. So your domain now is negative 1 to infinity, because nothing is passing negative 1 on your X. And your range, remember, is always negative infinity to positive infinity. Okay, and I wanted to do an LN graph. And notice this graph doesn't have an H or a K. And when we start our graph, we're going to do 1, 0, and your base, and 1. Our base, remember, is understood to be E. And E to the first power is 2.71, and all these other numbers behind it, but we're going to round it and use 2.71, comma 1. So I'm going to start my graph with those 2 points. .71, a little closer to 3. Now, the transformation here is we have a negative, so that's going to reflect over the x-axis. And then we have an A value, so all your A values, this is a vertical stretch. So, and if you notice, we have no K, so our asymptote is X, we don't have an H, so our asymptote is X equals 0. So the first thing you do is you reflect your points over your x-axis. This one stays. This one now would be 2.71, negative 1. And then we're going to stretch it by 2. So instead of this being at 1, we'll stretch it in, at negative 1. It'll be now at negative 2. And because it's upside down, it'll bend this way. So your domain is still h to infinity, so 0 to infinity, because nothing is passing 0. And your range is negative infinity to positive infinity.